project is the desulfurization of dimethyldiphene DBT by oxidative catalysis of titanium dioxide. Now, the reason I performed this project is because sulfur is one of the main contaminants found in the crude oil used to make gasoline. In the combustions of gasoline, sulfur is released into the environment. This sulfur reacts in the atmosphere to create acid rain, and it's known to cause a lot of respiratory problems. It causes a lot of asthma, bronchitis, and many of these problems that we see in humans today. Now, on top of that, the sulfur emissions released by crude oil and the fuels that are burnt cause about 2 million premature deaths per year. And on top of that, one of the things about sulfur and crude oil is that the EPA requirements for sulfur emissions is that you can't have more than 30 parts per million per batch in your batch of crude oil that you're making to make gasoline. So this is why desulfurization is very important. Let me start off by telling you what we did. We did desulfurization of DBT through oxidative catalysis of titanium dioxide to DBT sulfone. Now, DBT was used to simulate crude oil. The reason DBT was used to simulate crude oil is because DBT is one of the hardest substances to remove sulfur from. And a lot of engineers and chemists use DBT as a simulation in the labs. And what they use dihydronaphthalene, a chemical solvent used to dissolve the crude oil readily. Now, oxidative catalysis is a method that has been becoming more prominent over the years. Over the past 5 years, oxidative catalysis has become a surge. It's been surging. Now, the reason is because oxidative catalysis cuts down reaction times. It cuts down energy of activations, and it's overall more efficient. The only problem with oxidative catalysis as we know it today is the catalyst they have to use to make it work. The most popular catalyst they have in production in the companies that actually use oxidative catalysis is hydrogen peroxide. The problem with hydrogen peroxide is it's very expensive, plus it's very dangerous, it's very flammable. Not that crude oil isn't, but hydrogen peroxide is another added danger. Now, let me give you about an estimate of how much it costs for hydrogen peroxide. Hydrogen peroxide, about 10 mLs or 20 mLs, will cost you $200. That's just 10 to 20 mLs. Now, imagine if you had to buy about a ton of hydrogen peroxide. That would be millions upon millions of dollars a year just to be making and cracking your crude oil. Now, what we did in this experiment was, as I said, we got DBT and our dihydronaphthalene, our solvent, and we mixed that together. And then we introduced our titanium dioxide catalyst. Titanium dioxide, what we had to do with that catalyst is we had to figure out its energy of activation, how long it takes for the reaction to run to completion, and its conversion rate of DBT to DBT sulfur, which means how much sulfur will it remove in total. So, in the end, after we performed this project, I ended up finding out these facts about titanium dioxide. Titanium dioxide's energy of activation, 1, is 110 degrees Celsius. 2 was that titanium dioxide, its reaction kinetics, it takes about 90 minutes to run efficiently, about a 95% removal rate. That was the third fact, the 95% removal rate of sulfur containing compounds. Alright, so when you're performing this experiment, what you have to do is you have to heat up the solution of your DBT and your dihydronaphthalene with your titanium dioxide catalyst. And what this does is it simulates cracking, which they do in industry, and the oxidative catalysis process as well. And what cracking means is you get your long carbon chains that you have in crude oil, and you start making them to pentane, hexane, and octane, which allows you to burn them much more properly as they're shorter and more combustible, easy to react. So that's what they do, and they collect these precipitates in little flasks as they're producing them in industry. So that's one of the methods we used, cracking. Now, one of the interesting things about this catalyst was that the DBT sulfone, the sulfur that was converted and was extracted of the DBT, the sulfur-containing compound, actually precipitated at the bottom of our solution out of our NMR flask. Now, the reason that is important is because in oxidative catalysis with hydrogen peroxide and in industry catalysis that we know of, the sulfur never precipitates out. It's always in solution with the crude oil. So you never really get to exactly remove it, but it's not as prominent in your hexane, pentane, and octane. So you have a better removal rate there. But with this catalyst, it just precipitates all at the bottom of your batch. So now you can just remove that sulfur out of there. So that's another cost benefit. Now you get to actually remove the sulfur. So that's a much better environmental impact there. Now let me show you the graphs that we did to prove this. Here we have titanium dioxide and the rutile polymorph of titanium dioxide that we used. One thing you have to keep in mind is that we didn't use common titanium dioxide. We used a different titanium dioxide. We used a rutile polymorph. A rutile polymorph is a version of titanium dioxide that has been synthesized and converted a bit. It's changed in some geometric shape points. And the reason we do this is to lower the energy of activation for the catalyst. So as you can see, here are the main absorbance points for titanium dioxide. And here are the ones for titanium dioxide rutile polymorph. As you can see, they're just about the same. They're at the same place. So all the critical points are there. So for sure, it's still titanium dioxide. It's nothing else. We're not lying to you there. So that's figure 1, just to prove that. Figure 2 is the reaction kinetics study of DBT conversion at 135 degrees Celsius. Now, in your y-axis, you have your concentration of DBT, and in your x-axis, you have your reaction kinetics. Your time. And what we did here, we got a standard deviation plot, and we did statistical analysis with it. So we figured out how long does the reaction take. And on average, we ended up finding out that the reaction ceased at 180 minutes. So its optimum range was figured out to be about 90 minutes to 100 and 120. So that's about 2 hours total that you would have to run this reaction at its best. And that was figure 2. Figure 3 is a thermodynamic plot of kinetics reactions at 110 degrees Celsius, 120 and 135 degrees to decipher the energy of activation. Now the reason we had to do that was because we used the y equals mxb, and we had the lnk, the constant for the energy of activation, and we had to solve for m. And the reason we solved for m is to get the energy of activation, which we didn't know starting out this project. We didn't know the identities of this catalyst. As I said, we had to discover that through the experimentation process. So in the end, we ended up figuring out that the energy of activation that suited it best, its optimum energy of activation is 110 degrees Celsius. But it can also work at 125, 130, and 150. It works in between the 110 to 150 range. Its lowest temperature it can work it at is 110 degrees Celsius. That's 1/3 of what they have in industry. In industry, it's about 300 degrees Celsius with their unconventional catalyst. Now, figure 4, mass spectrum of DBT and converted to DBT sulfone. Now, this graph was made through GCMS, gas chromatography spectrum. What that does is it gets your DBT and it heats it up and it makes it into a gas. And you figure out how much how much mass in percentage is your carbon, your sulfur, and through that you identify the compounds. So you have DBT and DBT sulfone. And this is at the end of the reaction. This is after the reaction was completed after the 90 minutes. So you can see at the end of the reaction, you have less than 2.095 times 10 to the 5th power of DBT. And you have 8.38 times 10 to the 5th DBT sulfone. The number of DBT to DBT sulfone is basically exponential. It's 6 times more DBT sulfone. So our conversion rate at the end was 95%. That's a huge number. That's very cost productive, very cheap. And this is one of the reasons we're patenting the catalyst, the rutile polymorph synthesized catalyst. And this is the reason why I can't give you the methods for creating such catalysts at the moment. It would take me some time to be able to disclose that. Once it gets patented, then I'll be able to release it to Davidson Fellows. In the conclusion of this experiment, it's found that you have 95% removal rate with titanium dioxide, which means less sulfur emissions in the environment and less money wasted because the energy of activation is 110 degrees Celsius, 1/3 of what they have in industry. Plus, the reaction only takes 90 minutes. This is why this project is very environmental friendly and it has a huge impact on the world. It could help us produce more of our crude oil that we have here in America without violating EPA standards, which says 30 ppm per batch of crude oil. So now we can make our own batches out of our own crude oil. And the reason is because in America we have a lot of crude oil. The reason we can't use it is because if we used it, we would violate EPA standards and we'd be charged fines by the EPA for producing that crude oil into gasoline.